So what we'll do is first we'll go down the line in a minute, ask people to introduce themselves, what they do, who they work for, and why they care about 5G. There's a few things I think we can start to talk about. We could probably start at the top with bandwidth. You know, what opportunities and challenges especially does that present, because we've got techie guys here. But then drill down into low latency stuff, and then we can talk about applications and things as well. So we've got till 12:30. Is that roughly? Yeah. Okay. So, but obviously we'll have plenty of time for questions and open up. And Robert is presenting this afternoon after lunch as well. He's got cool stuff to talk about, like robots and AI and things. So we won't preempt too much what he's going to talk there, but try and continue the conversation. So you want to start at the end, who you are, what you do, who you work for, why you care about 5G, and yeah, let's start there.
And how amazing your PhD advisor was.
Thanks, Iain.
Very subtle.
Very good.
So I'm Salam Akoum. I work at AT&T Labs here in Austin, in Arboretum. I work in the Advanced Wireless Technologies group. What we do is basically standardization, research, development, test beds, friendly user trials, all related to 5G. I mean, right now. So basically, standardization part, we are very involved in current standardization of 5G release 15, release 16, currently ongoing, release 17 planning, so on. We also do we develop our own hardware as well to test some of our algorithms and the features that we care about to put in our network. We also have our own kind of channel sounders to measure channels and see how millimeter wave performs, how these channels look like, and then also part of our teams is involved with all our vendors like Ericsson, Nokia, Samsung, so on in friendly user trials. So we work with them to kind of figure out what kind of speeds you can get with 5G, what kind of latency, so on. So this is what we do as a group, and yeah, and I graduated from UT with a PhD with Professor Heath back in 2012.
So now I've been to the labs up there, but it was always to see devices when I was there. But you do base station equipment as well as devices, right?
Yes.
Yeah.
Yeah.
Yep.
I mean, yeah, there is a team there that does device testing.
Right.
But what we do is more on network equipment side, kind of, figuring out what to put in our network and why.
Right. And since the pressure's on here, so what was your PhD actually in? Keep it simple, because I know you guys can go off. Yeah.
Let's see. I'm trying to remember. It wasn't that long time ago. It was about multiple antennas.
Okay.
And cooperation between different base stations, and when to do cooperation and when not, and what kind of gains you can get from that, with imperfections in the channel feedback and so on.
All right. Cool. Okay. Robert, two Roberts on one panel.
Is this on?
Yeah. Yeah, you're okay.
Yeah, my voice is loud enough anyway. Yeah, you can call me Bob. This
I think
is how we differentiate each other.
You'll need to use microphone for the online group.
For the online?
You
can hear it?
Yeah.
Okay.
Yeah.
Yeah, so we can differentiate. I'm Bob, he's Robert. That's how we've kind of worked through this. But yeah, so I work for PHAZR as a co-founder and a vice president. So we were one of the early companies in 5G millimeter wave technology. But before that, I really have been a millimeter wave advocate since around 2007, maybe. So when Robert and I first started working on millimeter wave technology, we wrote a book on millimeter wave technology. And then that led us into some of these entrepreneurial efforts, and PHAZR was one of those. And yeah, so at PHAZR, as I mentioned earlier, we're developing base station technology, user equipment technology that really leverages millimeter waves and meets all of the 5G criteria that Iain listed in terms of high bandwidth, low latency latency latencycy. So yeah, I mean, really, I'm really in the middle of the engineering tasks to build these systems, to make these systems work.
Okay. PhD?
Yeah, so my PhD actually was a very sexy topic. It was in very ahead of its time. Online learning for link adaptation in multiple antenna wireless systems.
Wow.
So really some of the streaming processing that's real hot right now.
Yeah.
We were doing that, what was that, 2008, 2009?
Yeah.
So.
Yeah.
I'm feeling really, really underqualified here. Prof, you're up.
Yeah, so I'm wow, I got a lot of volume here. So I'm a professor at the University of Texas at Austin, and I'm working in multiple antenna wireless communication. Some of you might remember I spoke here a couple years ago about millimeter wave and connected vehicles. So my group right now, I have somewhere on the order of 10 to 20 students, I think hopefully closer to 10. Try not to think about it. They're looking at millimeter wave fundamentals, so this includes like the signal processing aspects. We're looking at some of the ideas are how 5G could be better. Some of the things we've done, we think 5G should have done it that way. We look some at channel modeling, performance analysis, and we're also trying to imagine what 6G might look like and how we can do something that's a bit more disruptive in the physical layer than what happened with 5G, which was basically let's tweak 4G and just give it a new name and add some bands. The other direction I'm looking at is a little more application focused. So still doing a lot with connected vehicles, and I saw a lot of the comments here about how many base stations we might need to support the connected vehicles on the road, but I think that there is a lot of advantage to exploiting connectivity in parallel with automation, and that's not being leveraged right now. And 5G has the potential to bring that into the market, and that's going to make the automated vehicles operate much more safely and efficiently because they'll be able to exchange information. So I have a number of students working on that, and then as part of getting into automated vehicles, I realized there was a lot of connections between millimeter wave communication and automotive radar, which is an important sensing component. So now I have a couple students looking at joint communication and radar sensing as well, and even one student looking at computer vision, though we have got sidelined in, we were looking at pedestrian detection and tracking, which has been done quite a bit, and he's sort of morphed into analyzing basketball plays and trying to quantify the value of different players. I'm not quite sure where that's going, but it sounds pretty cool. Don't know 5G's role there yet. Yeah, so I think that's a good introduction.
Yeah, that's the first. I have never heard anybody link 5G with basketball, but that's a good.
Yeah,
one.
there's a big market apparently for sports analytics, and anyways, I think there's a lot of potential there. It's just hard to measure.
Yeah. So there was a demo last week. I was at CES, and Intel has done this demo the day before with the NHL of a stadium with 5G with edge compute in it and analytics, and you can bet throughout the game in the stadium, literally play by play, and you can like bet where the puck's going to be and stuff like this. And it's all they say, oh, it's just nano betting. It's just a few pennies. But when there's like 10,000 people betting on 100 things through a game, the money. So yeah, you could be, the application could be, will LeBron make this shot? And your analytics say that statistically he's not going to when he takes off from his left foot versus his right foot. But I don't know.
Actually, that's a really good idea. Looking at betting, I haven't thought about that, but there's money there.
Oh, there's money.
Wow.
Oh no, there's my kids, my son is like, no, there's money there. Trust me. All right, so let's go back to the other end. Let's talk about millimeter wave. Let's start at the top and drill down to the lower bounds. So I want to put millimeter wave in today, right? Obviously, you guys are doing it. What's the biggest challenges today with this if you're deploying? Okay.
So, I mean, millimeter wave comes, it has a lot of advantages, huge bandwidths, but also has a lot of problems. The signal doesn't go very far, so you need to densify. So you're putting small cells from day one, basically. And you need to take care of you're adding a lot more antennas, and the antenna aperture is small as you go. Wavelength is higher, but that means that your beams become very narrow, and then you need to do a lot of what we call beam management. So now you're dealing with a beam-based system rather than LTE was cell-based system. So everything you do from control to initial access to everything is actually based on beams. And you need to figure out to align the beams between your transmitter and the receiver to make sure that the signal goes through, and deal with also one of the main problems of millimeter wave is indoor penetration loss, but also blockage. And blockage is like a really much more worse form of shadowing, but it occurs at a much faster pace. So you need to figure out how to get rid of that blockage, and blockage can be self-blocking. By just carrying your phone, you can block yourself, or it can be from something passing by. So to deal with that, you also need to kind of recover from beam failure and do it at a faster scale than what we do right now in LTE, like handover and so on. So all these issues we have to deal with, going to millimeter wave. But of course, there are advantages that we can talk about later.
Okay, so with LTE, you said it's very cell-based. So my phone had a connection to this cell for transmit and receive, but we didn't worry too much about the antenna had to obviously radiate and receive, right? But it is relatively, I want to use the word dumb here, but it's a relatively simple antenna. What you're saying now is that the intelligence here, the processing is now down at the antenna level. So now I don't just connect to that antenna, my phone has a specific beam to that antenna. So from an equipment point of view, because these guys are all valuation guys, has the value shifted from the pure base station as more of that processing and that, I'll say intelligence, but more of that workload, is it now done in the antenna? Or
I mean, you need both. You didn't.
Okay.
I mean, you have a lot more going on in the antenna to make sure that your beams are done right, but you also have a lot of baseband. Yep. That you need to make sure that it's there.
Yep. So, Bob, are your antennas more expensive as a result now? You've got all this equipment in there. You showed pictures of them and these nice planar arrays.
Right. I mean, of course, there is a cost initially when you deploy these things because the complexity is increasing, and so therefore there's naturally going to be a premium for that stuff. But I should mention that all this advanced beamforming technology and beam steering technology, it's not new necessarily. It's just that the scale of it now is increased, and it's a lot more critical. So before, when we were beamforming, which we were doing in LTE, but if it wasn't quite right, it didn't matter necessarily. You would still get some signal. It may not be optimal. But in millimeter wave systems, you don't select the right beam or select the right beam source. It could be really critical for your link. So in that sense, I think beamforming is more critical now than it has been before, but it's not necessarily new. It's just the dimension is higher. Taking a step back, though, from millimeter wave, I think the thing that I always try to remind myself when I'm thinking about millimeter wave, because there are sometimes you get into these discussions like, is millimeter wave going to happen? Is millimeter wave the solution? Should we just stick to our sub-6 gigahertz bands and increase the technology there as much as possible? And the thing I always come back to is, well, okay, maybe that'll work for a small amount of time, but eventually you're going to have to go up to these bands because that's where the bandwidth is available. There's only so much left in the sub-6 gigahertz spectrum. A lot of it has been auctioned off. A lot of it is already in use. We're finding new ways to find more and more spectrum at CBRS band. There'll be some new bands above 5 gigahertz probably, above 6 gigahertz. But in general, we're going to have to migrate to millimeter wave. So we better figure out how to use this spectrum the best way we can. And I think, all of this intelligence really will reward us in the future. That this is not going away. This is here to stay. This is how networks are going to have to be deployed in the future if we want to keep increasing its capacity.
Good. So, biggest challenges millimeter wave today? I want to put it in. Is there anything your students are working on to address those immediate needs?
Well, I think you got two people a little bit closer to the implementation than me here, so I'm not sure.
I'll rephrase the question. How far out do you look? So what's tomorrow to you?
I mean, tomorrow, we are interested in more than 2 years out. I mean, we're looking 2 to 5 to 10, depending on the interests of the sponsor and the funding source. And and I mean, look, it's flexible, right? I mean, the companies don't want to fund stuff that's 10 years out because they want to sell it to their management, that it's going to have an impact. But at the same time, the students can't really do a PhD on something that's 1 year out, because by the time they get up to speed, that 1 year is gone, and we didn't do anything. So it's something we have to do that's very careful. And so what I want to do is, there's a lot of smart people who are working on developing the 5G standard, and I actually don't want to get stuck in looking at their contributions and try to differentiate there, because I think they are putting all their time on that. My students are taking classes, they're doing other things. So we also look further out to get some more strategic advantage in the work that we're doing. And we're not competing with the companies that have much bigger budgets than us.
And the companies drive the standards. I mean, they'll do that themselves. So,
Right, yeah. I mean, there's no incentive for an academic to really participate. I mean, if I had a bunch of patents, why would any company put my stuff in the standard? They just all have to give me royalties. Whereas if they each put their own patents in, they can trade with each other.
Right.
So.
Yep. Okay, so you guys mentioned release. We're obviously at 15. You mentioned release 16, 17. So timing on that. When do I said release the new core starts to come late 2020, 2021. So when do we get release 16 standard, and then release 17? And let's talk about second part of the question is, what's the difference between 16 and 17? That's what's in there.
Okay, so release 15, well, there was 2 parts of release 15. There's the accelerated part that Iain mentioned in his presentation, where we really wanted to get the standard done so that, we get to implementation fast. And it was really fast implementation. If you think about it, like 6 months between the standard was out and actually AT&T has, network on right now. So that was the June 2018?
18.
What year are we
18,
on?
yeah.
Okay. So that was the non-standalone, and then there was a freeze for standalone as well. And then release 16 already started, and then expected for the physical layer part, the RAN 1, we call it Radio Access Network Group 1, for December 2019 to be done. And then the ASN.1 the freeze of the release will be in June of 2020, and then the proposals for release 17, what's going to be in it, are going to come in December 2019. So that's usually the standards are 18-month cycle. So the releases, I mean.
Right. So if we have release 16 frozen somewhere around middle of next year, what's the fastest you can get equipment, or you'd expect to have equipment ready? What to put in?
I mean, right now we have equipment based on release 15, and then towards the end of the year will be available. So, I mean,
6 months.
yeah.
Yeah. Okay. So, Bob, so you're supplying the equipment, right?
So when it comes to standard, I'll defer to her on that as far as timing and features. We just implement it. So release 15, our products are coming out in Q2, Q3 of next year. So right now we are actually using, we are trialing some release 15 equipment, but we are not actually deploying that. We have this pre-standard stuff that we had previously.
Right.
So as far as the turnaround time for when a new standard comes out, I mean, it really depends on how much changes there are, but generally speaking, the changes don't necessarily have to be that much. So you can turn these things around pretty quickly for the new releases after you get started. So 6 months to a year after a release, I expect you can have that.
Yeah. So a lot of the 5G stuff we had in 18 was, of course, pre-standard, and
That's right.
It was, which is confusing. So, so
Also
release 15. Here we are, beginning of 19. Release 15 equipment will still be going in 2020, right?
That's right.
Release 16 will be going in what, 2021, 22. 17 will be late 22, 23. So that's 5 years from now, 4 years from now. Yeah, we've got a pretty good roadmap and a long way to go. So, okay.
Yeah, it sounds very, very intimidating. When you're saying it.
Yeah, you can say.
Well, actually, I wanted to, if I can ask a question here.
Sure.
So I felt that in your presentation that you were a bit pessimistic about the losses of millimeter wave, because like the rain and penetration. I mean, I know that there are those losses, but I mean, for small links, I don't feel like it's a huge issue. But I guess I wanted to see if we can get feedback from Bob and Salam, because they've been trialing the millimeter wave stuff to see, are you guys confirming the severity of millimeter wave working in the Northeast, or do you want to push back on that? I don't know what the answer is, but let's see.
And I have an answer as well, but I want to hear those.
Oh, okay.
I mean, I know the trials that we did in Austin and Waco, which is not really Northeast. And that was the millimeter wave actually performed quite well. So.
Yeah.
But did you see the severity of foliage, or is it just not an issue where you did the trial?
I don't think it's as big of an issue as Iain mentioned. Like, it's not the drastic problem, but I actually can't comment on exactly what foliage we had in there specifically, and what kind of rain absorption and all that. But yeah.
So I can comment a little bit on this.
Yeah.
So one of the interesting trials that we conducted was a simultaneous trial, 3.5, 28, and 39 gigahertz. So all three at the same time, same trial locations, with foliage and with weather events. And one of the interesting things, there is additional loss associated with millimeter wave, but it's actually not that much. Depends on the density of the foliage. But what really hurts you is if the foliage is wet. So if there's rain. So when rain occurs, that foliage gets covered with water, and then millimeter wave, you see a big gap in the performance. So what that means is that millimeter wave is a more dynamic environment. You're going to have to consider the fact that the propagation that you see today may not be the propagation you see an hour from now. How does your network deal with that?
Right.
How do you deploy for that? I mean, these are things that actually are very exciting from an engineer's perspective, because you're like, oh, I'm going to reconfigure the network very, very often. And those are some of the things that we're trying to introduce as technology into the system. So, yeah, I mean, there is a loss. If you want to speak about dB, a few dB loss from millimeter wave compared to, sub 6 gigahertz spectrum, depending on that frequency as well. But once it gets wet, there's a more substantial effect. And of course, the density of foliage matters. The type of foliage matters. So if there's a lot of water in that foliage, then that's even worse for millimeter wave than it is for sub 6. So it's really hard to make a blanket statement like foliage is bad for millimeter wave or foliage is not a problem. To me, it's a very gray thing. You have to kind of look at each scenario. Where are you in the United States? What does that foliage look like? Where are your base stations in terms of their height? I mean, there's a lot of factors. But I do think they're all workable. And again, I do agree with Iain, and to some extent, it is more of a nomadic in the beginning than a mobility. You're going to have these pockets of millimeter wave that you start out with, and then eventually you scale up to get to a point where it's universal.
Right. So what in that trial? What were you putting over the air? Was it video, or what were you?
I mean, we did all sorts of data. This was, most of the time we're just hammering the links, right, trying to see how much we can push. But we did do video quality assessments and that kind of thing. So yeah.
So if you were a consumer and it rains, what would you have seen?
It depends, right? If you're watching a video, most people think they need a really high data rate for video, but actually most of the time you don't. And so you probably wouldn't see much if you went from 100 to 10 megabit per second. Right. If you went down to 1, you might see it. But that wasn't something we experienced in those trials. And again, you can question the layout and everything, but it wasn't too big of a drastic effect. So.
Yeah. Okay. Yeah. So my answer, it's a good question. Yeah. I actually have more slides on that. Is you have to engineer around it, right? So putting millimeter wave into Tucson, Arizona, is flat, right? Not many big trees, et cetera, would be a very different engineering challenge from like Ithaca, New York, where my parents live. You can do both, but they're going to have different requirements, and then the cost and then the cost comes out. So everything we did was cost-based. Into what the question we always got was, what was the cost of deploying millimeter wave? Well, the answer is it depends on what you're trying to do. And we actually had 9 different factors that come in, including trees and foliage and hills, but it's also population density, type of housing, how the housing is constructed, the housing density. So if the houses are too big on too big an acreage, you can end up with literally one cell for 2 or 3 houses, which doesn't make a whole lot of sense economically. And then the population type, if you have more kids, more demand of bandwidth, et cetera, et cetera, et cetera. And then the final one was, is there already fiber to the home in the neighborhood? If there is, don't bother, because everybody's got fiber anyway. And then also, how much competition is there from an ISP? So if you've got 2 or 3, I've got a choice of one cable guy and one other telco who can give me 45 megabits per second. My neighborhood's pretty good for millimeter wave. It's got other issues. But if you've got 2 or 3 good competitive ISPs in that market, why would you bother building out, especially if it's got other factors that count against it as well? So it's an interesting, that's why it was 26.2 million households. It was really fine criteria, and you have to use all the population densities and things like this. So it's a good question.
So I mean, is the main cost there? It's really just density of infrastructure. Is that it?
Yeah.
You have to tweak that based on all the other stuff.
Yeah, it's cost of putting in a pole, how high the pole is, which pole I can use. I need fiber there to get to the pole, but I don't want fiber to the home.
Yeah.
Right. So I need enough fiber to get to it, but not too much fiber. It's competitive. What's the cost of getting the fiber in? Is power, et cetera, et cetera, et cetera, et cetera.
So actually, that brings up another question for me on the penetration losses indoors. I mean, Bob, I saw the units that you had were mounted outside, and I know there's always this discussion about the loss, the materials of the building. So I mean, do y'all have any insight on how it's going to work how different 5G things are going to work inside, and do you have to be outside? And
Yeah, exactly. So one of the products that we initially had was an indoor CPE. So the idea would be you'd put that maybe on your wall inside or on the window. But for a lot of the early trials, the customers were just interested in getting as much performance as they could, so they didn't want to try something like that. But what you'll see is that e-glass, for example, is very difficult. You can't get through that. It doesn't matter if you're sub-6 or millimeter wave. You can't get through it. So that stuff is very challenging. And in fact, if you want to deploy these things inside, you end up finding that like very unintuitive placement for your CPs inside your home to get the best performance. And I think there might even be some of this online from some of these Verizon deployments. You see some people talking about that. So
Verizon's goal actually originally was that they would drop FedEx to you as the homeowner, the equipment, and you would literally go to a window and stick it on and push a button, and they ended that because people are putting it on the wrong window, or people would put it on a window and their spouse would say, well, that's ugly, that can't stay there, put it on that window. Or the e-window, especially in Texas, because remember they were doing Texas as well, so we get the e-windows all the time.
And another consideration is when you're transmitting at millimeter wave, the safety requirements are a little bit different now. And in order to get really good performance, sometimes the power is boosted, and then that means that the people can only be so close to these indoor CPs, and so there's some safety. There's a lot of panic around millimeter wave. People aren't sure what the health ramifications are. Of course, science says there's not much, but it takes a while for the industry to get comfortable with this technology being closer to people. So there's a lot of factors that go into why you haven't seen the indoor stuff as much lately.
So any questions we said we'd open it up. Yeah, Jim.
So this is not a sexy topic. Can you kind of go into security? As I understand, that's a big issue with 5G. You got autonomous vehicles, you don't want that 400-pound guy in the bed hacking your vehicle and crashing it.
But it's also the Huawei ban. So can you discuss this security problem with 5G and how that may inhibit the deployment?
I mean, I can't talk about the applications as much, but I can talk about the infrastructure. There certainly is a huge push to be using U.S.-based, U.S.-sourced vendors for infrastructure, for obvious reasons. I mean, you saw all of this news about Huawei recently and the security concerns there. but the reality is there is no major U.S. infrastructure provider at this point for cellular technology. So we're kind of in a pickle, right? We have to figure something out for that. So yeah, I mean, that's a huge opportunity, obviously, for us as a company to come in and try and establish a place in the marketplace, because then we can provide an alternative where a U.S.-based company can actually be used to deploy infrastructure for 5G.
So from AT&T's point of view, in the labs, is there a security effort within the lab specifically, or?
Within the labs, I'm sure. Within my group, we don't really work on that. We're more focused on the radio access network and not really security related, but definitely it's a very, important concern, and something that's definitely being addressed another group in the company. But I mean, in terms of Huawei, I mean, right now our vendors are Ericsson, Nokia, and Samsung for 5G. So,
right. So you raised up a good point. Is security gets raised a lot, but the security of the air link between the device and the radio, right, is actually not as much as the problem as somebody hacking into there's those Amazon drones trundling around yesterday. You can see somebody getting one of those, stripping it down, using that to get into the network. It's not a case of hacking into your network through the radio network. It's accessing through other points, right? So that's where the hacking a radio link these days is, boy, good luck. Have fun.
Yeah, imagine if they start hacking the remote surgery. That could be a problem as well.
It could be a big, yeah, but it's right. The weak link is the connections on either side.
That's right.
Yeah. How many people give their passcode on their phone to somebody else, their spouse or? No? Yeah? The AV guy. So. Security, I don't think will go away, Jim, and I don't know how to phrase that. The concern about security today is more, I mean, there was a security concern there with 4G as well. It's no different. Now it's been raised a lot because of the relationships with Huawei and things. And
well, I think the security is raised because of the potential uses of autonomous vehicles and surgery and all that. Now you have a greater concern because things that crash down or something crashes. What happens to your car? Or your heart?
I have a couple of questions. So then it would be safe to say that over the next, sounds like several years, we're going to have some 5G equipment, some 4G equipment, and some 3G equipment at a lot of cell sites. Still, I would expect.
yes.
The other thing is, if the antennas and the radio are all going to be in one unit and it's going to be on the tower, is that going to cause an issue, a practical issue at a lot of towers where a lot of antennas are going to have to come down just due to weight limitations?
So, I mean, if this is to address the presentation that I had earlier where I talk about a totally integrated unit, that is maybe something that it's not necessarily unique to PHAZR, but this is something that is one of our promoted innovations. Is we believe that is the way this is going to move in the future. But there is still the old model where you have front haul up to the base station, so you wouldn't actually necessarily have to replace the entire tower element to upgrade. But you want to comment more on that? I don't know.
Yeah. So. There's a lot of, also there's a, the front haul, but then there's a central unit, and then there's a distributed unit, and then, I mean, there's not necessarily everything needs to go on the same place at the same time. And definitely we will be having 4G and 5G for, together for a long time. And then 3G obviously is right now still there, but, gradually decreasing and sunsetting.
I think everybody in here would probably agree that there's a lot of antennas on a lot of towers that just haven't been taken down just because it costs money to retire those things. So I just wondered about the weight issues. The last thing I want to ask is, autonomous vehicles the autonomous vehicle that will travel across country is probably not going to be a result of 5G. Would you agree with that? It's going to be some additional iteration. I mean, we're not going to transport freight, or I'm not going to go to sleep in my car in Atlanta and wake up in Los Angeles.
Yep.
Or, I mean, that's not going to happen, right?
Yeah, so there are different, I think Professor Heath can comment more on like the different levels of how to reach autonomous vehicles, but in terms of 5G new radio, what, the focus on in terms of standardization to enable on the road to autonomous vehicles is remote driving. For example, someone sitting at home and driving the car. That's Iain also mentioned it in his presentation, and that requires a lot of small latency and high reliability. There is also platooning, with the vehicles or the trucks driving behind each other, and there's like one main kind of manager for them. There is advanced sensors where like vehicles share information between each other and kind of share like their point of view or what they're seeing. So all of these will be enabled by 5G by just making the network faster, more latency lower, and more reliable.
Somewhere down the road, right?
Yes.
Yeah.
Yeah, I expect Robert has a lot of comments on this topic, so I'll be brief. But my perspective on all of this is, autonomous vehicles right now don't really leverage too much the wireless network. There is some, but most of it is vision systems, positioning systems, radar systems, and how much it starts to exploit the wireless network, the 5G network for autonomous driving is yet to be determined, as far as I can tell. Would you say that's accurate?
Yes, I think this idea that a car is going to be connected to 5G while it drives you from Austin to LA, I forget your specific example, that's probably not going to happen because it's going to be a long time before 5G is deployed with that much density in any form. But what I see is that the value of connectivity in many of the situations that are most challenging for automated driving occur where there's a high density of people. So driving in downtown and on the campus, especially with all these wonderful scooters around, is a nightmare. And driving on, I-35, okay, it's annoying, but I mean, the trucks and the cars, they're all going in the same direction, and if it's backed up, we're all just sitting there backed up. So I don't believe that you need to be connected for automation, but that connectivity is really going to enhance the automation in the urban areas, and these are the places where you can get a lot of value by sharing sensor data. Oh, the truck ahead sees there's an idiot scooter here, so I can take evasive action. All of this stuff, and that's going to happen coincidentally where there's a whole lot of people, and that's where AT&T wants to put their infrastructure because those people are their customers. And so I think it's going to work together, but it's not going to be a pure 5G only solution. It's going to work.
My wife and I went out to the Davis Mountains last week and 2 weekends ago, which is West Texas, where the McDonald Observatory is out there, UT's observatory. If you haven't been, it's well worth it. A lot of people book tickets at the McDonald Observatory. They have these star parties, which are fantastic. They book them and then go to the campus up here and knock on the door, and there's a sign in the astronomy department saying, yeah, the observatory is 6 hours that way. Happens all the time. People come in town and don't realize that the observatory is in the mountains where it's dark. But anyway, there is no 3G service in West Texas on I-10. No, I'm not in the mountains. There's nothing. But on I-10 between here and LA, and I've driven it many times with my son, I'll tell you, there are long stretches with no 3G where your phone has 0, and not for 5 minutes. I'm talking for 20, 30 minutes. So, exactly what your point is, that it just makes no sense. There'll never be 5G out there. It makes no economic sense unless there's some super huge high value traffic going on I-10 for some reason that needs monitoring all the way. So, I know that you've got one more question. You've got a question. I'm going to hold on. One other point on the antennas I was going to make as well is you said there are antennas up there that are still up there and we're adding weight. So the reason antennas get replaced today by the operators is really three factors. Number one, it's old and they've got more stuff to put up there, and they don't want to exceed the weight allowance on the tower and have to pay for the tower to be reinforced or replaced or etc. So it's an economic reason they get replaced. Second reason is they're just old. We used to replace antennas about every 10 years when the squirrels had eaten through the casing and all the rest of it. But the main reason today is combinations of bands. So as operators get more bands, AT&T's putting in FirstNet, for example. They've got that was a new band combined with AWS and some other other spans they got. So it made sense to put in a new antenna that had new combinations. So you take down two antennas, put up a new one that has the combination of both. Well, now look at I'm simplifying. Now put the combination of what's coming. CBRS, I mentioned, 3.5 gigahertz. You'll be able to buy licenses for that hopefully later this year. That'll result in a new antenna. Bob, you mentioned other bands like C-band, 3.7. We can probably use other antennas for that. You used to mention other sub 6 gigahertz. Every time that happens and somebody grabs some more spectrum, the same thing's going to result. T-Mobile Sprint combination, new combinations of bands that T-Mobile doesn't have, i.e. 2.5 gigahertz, will result in a lot of work on antennas. So usually it's the bands and the economic reasons. But antenna used to be a completely boring subject 10, 15 years ago. Nobody ever talked about it. Now we all talk about it. So, Ruben, you had a question.
Yeah, I wanted to talk a little bit about spectral efficiency. I know, my limited understanding is that, our iPhones can only process so much of the spectrum itself, and that as a result, we've reached that limit, and now we've effectively solved the problem by just throwing spectrum at the problem. Is that a kind of a correct understanding? And if so, do you ever see us overcoming that spectral efficiency barrier that we're in now?
So you're talking about how efficient we can be with a piece of spectrum, how much data we can get over it. That limit's been reached, and therefore we need more bandwidth to get higher speeds.
Right.
Right?
Well, Robert, didn't you have a paper on this?
Yeah, a few dissertations as well, maybe. Just as a comment here, so there's spectral efficiency, but we have to look at exactly how that's being normalized. So what people usually care about, it's the spectral efficiency, something like per kilometer or per user. And so we could be using the spectrum with the best possible coding and modulation, and we're getting all the data rate out of it. But everyone in here wants a piece of that. And so when we divide it all up, the net throughput you get is small, even though the spectral efficiency is very high. And so then what are ways to solve that? Well, we could deploy a whole bunch of infrastructure. We could use massive MIMO. We could use millimeter wave and point beams. So there's also this element of reuse. And reuse is a core principle in cellular. So when there's a lot of people in this area, we put more base stations there. We split up the people to different base stations. They get to use it at the same time. So that's the key thing that we have to remember. Now, what you're saying about efficiency, in a single link, we do have approaches, not considering interference, that give us the theoretical, very close to the maximum rate that you could get. But we still have the fact that everybody wants to use it, the spectrum's being reused, there's interference, and so those become significant challenges. And then the dimensions to overcome that, so there's more infrastructure, there's more antennas, and then there's more spectrum. And so more antennas is millimeter wave, massive MIMO, talking to multiple people at the same time on the same spectrum. So that's spatial frequency reuse. And then going to millimeter wave is really just about throwing bandwidth at the problem and getting a higher peak rate. And you can't get a high peak rate. No matter what you do at the lower bands, the best case situation is where you have the cell all to yourself. But if you have only a megahertz of bandwidth, you're going to get just a few megabits per second. You're not going to get a gig, even if you have the cell to yourself, because the bandwidth limiting you. So there's like pushes on all these different fronts, you know, to reduce the people in the cell, to get more people served at the same time. But then at the end, you're left with just bandwidth. And that's what the point Bob was making earlier. I mean, you have to have bandwidth to get the high rates.
Is interference worse at millimeter wave? Are there more interfering sources? So obviously you get interference from signal reflections and things like this in practical terms, or is it as good or bad as the sub-6?
Well, that's the one of the good things about millimeter wave is this, you know, the beams that I was talking about. So if you go narrow beams, then your interference automatically decreases because, you know, you're very pointy.
Right.
So that's, you know, a good thing with that. So you get some scenarios where you're noise limited instead of interference limited.
Right. So see, in 4G, I would send out a signal to this entire room and get interference from multiple sources. But now I can send a beam right at Gary,
Exactly.
and the interference is only going to come from his neighbor or...
Yeah, so you're limiting the sources,
Yeah.
right? I mean, of course, there's interference and you need to deal with it,
Right.
of course, but...
Yeah. Yeah. Okay.
I mean, yeah,
I was
it's
going to say...
not much more I can add on that.
Mhm.
If you're focusing your energy in a certain area, it's not going to interfere with people as much, right? So it's
Right.
a very intuitive way of looking at these systems. You can kind of think of it as, you know, kind of like flashlights, right? If a flashlight is pointing around, it only sees in a certain direction. It doesn't illuminate areas outside of that.
Yep. Yep.
So light bulb versus
Yep.
flash, I think.
So we went from 2G, which was what TDM based, TDMA, right? We went to CDMA 3G, then we went to OFDMA 4G. We had improvements in efficiency at each point. Is there anything what's next after OFDM? You mentioned 6G and changing the air interface. Is there a next step function beyond OFDM that is more efficient, or is it just a matter of getting more beams, more reuse, etc.?
Yeah, I mean, my interest is about making it more efficient accounting for the hardware. And so we have a project with AT&T actually on this where we're looking at the use of large antenna arrays but with low resolution data converters. And that device, the digital to analog or analog to digital converter, when you go to wider bandwidths and have lots of antennas, it's a huge source of power consumption. And so the way the system is engineered now is you have the precision of that converter is decided based on, you know, making many trade-offs and working with the algorithms, and so it's several bits and it's a lot of power. And so as a result, you end up having to make compromises. The beam-based solution in 5G is such a compromise. We know from LIMO that that's not the best thing to do, to form a bunch of static beams and assign people to it. It's not necessarily a terrible thing, but it would be better just to form beams to everybody and however they look is exploit all the multipaths. When you go to the beam-based approach, you miss multipaths, and that's fine at millimeter waves, but not as good as at lower frequencies. So what I'm interested in is how could we redefine the standard to use many antennas, but with this ultra-low resolution, and make all of the fundamental parts of cellular still work. So the synchronization, the training, the handoff, all those become really challenging when you have like 1 bit of quantization, but you can overcome it. And so the theory says that, yes, it's possible. And so now we're trying to figure out how to flesh that out into something that is more general than the simplistic, you know, formulas we use in the theory, so to make it work. And that's going to make a major change. So and then the physical interface probably would be a single carrier, not OFDM.
Okay. All right, good. Yep.
Yep. Got a quick question back here.
Oh.
So if we can just step back when we talk about households, I mean, you mentioned 26 million, 26.2 versus 30 million households on this millimeter wave aspect of it. So that's the household perspective. But then there's also the business perspective. Can the panel give us a little color walking through spectrum from millimeter, how that's covered by household and business? And then as we go to lower bands, right, and producing this 5G technology, how that is penetrated in the household or the business component to make the money case.
Are you bidding on millimeter wave spectrum right now?
I have no comment. Quiet period.
So, okay, so the economic discussion from millimeter wave down to 600 in Steve's case. So where, actually, we'll start from your perspective. Where do you see millimeter wave being applied to a use case, right? Do you see the entire United States being covered in millimeter wave? I would think not, but what's the use case for millimeter wave? And then as we get into the 6 gig, sub 6 gig all the way down, how does it all break out? So it's, we've got tiers now, right?
Yeah. So obviously, 5G is not only about millimeter wave. It's also, it's millimeter wave plus the sub 6 gigahertz bands, and that's from day one. So millimeter wave, you get a lot of bandwidth. You can have huge data rate improvements. So you would think, hot zones, gig zones, or whatever they're called, where you need a lot of data. You can also use it for, of course, V2X, vehicular communication in urban environments. You can use it in factories, industrial IoT. You can use it in hospitals, stadiums. We're demoing and trialing all that. But also, you would need the sub 6 gigahertz for coverage. Right now, with the non-standalone, basically you rely on LTE for coverage, and then millimeter wave for increasing your data rates. But then, moving on, you will also have coverage using 5G, but on lower frequencies. So.
Okay.
Yeah, if you want data rate and lots of it, then millimeter wave is a good place to be. If you don't, if you care more about latency, then of course the lower frequency spectrum is going to serve you probably better, because you can suffer less capex for the same performance if you don't need a lot of data rate. So I would say, it kind of, there's a sliding scale there, right? Like, how much data rate do you need, and how much connectivity do you need, and how much infrastructure cost can you afford? So it naturally lends itself to those applications.
What's the biggest location or area you guys have put millimeter wave into?
Define biggest, like, what do you mean?
Like
Meter
covered an
square?
entire city, or
okay, so the scale of the deployment is what you're saying.
Scale,
okay.
yes.
So neighborhoods. So similar to what you were talking, a little bit bigger than what you were talking about with the
So more than 3 houses and 2 streets, or
neighborhoods, subdivisions.
Okay.
Yeah.
Yeah. And all the way down to factory, house, obviously.
Right. You can even do similar use cases like with backhaul, right, where you just have you're servicing just a few customers.
Yeah.
Over long distances.
And that's been done for a while.
Yeah.
Shoot the beam. Right. Okay.
I want to comment. I think there are many applications of millimeter wave spectrum, but there are also a number of compelling use cases for the lower frequency. In particular, many of these IoT devices that were you mentioned, Iain. Those are inside. Most of them. Think of all the ones that we're wearing, and we're inside right now. And so if we don't have a solution for the penetration problem, and people aren't willing to deploy a 5G cellular network in their house, then you're going to need to get those signals from outside. Okay, yes, you mentioned many of those were Wi-Fi, and people do have Wi-Fi. So maybe that's a hack, but there's a number of things where IoT is going to need to get longer range and penetration, and that lower frequency is valuable for that. And it doesn't have a lot of bandwidth, but if you're just pinging the toilets every minute, you don't need the bandwidth. So,
yeah. Actually, I think the application's inside. And actually, Bob, you mentioned about those windows. You were talking about reflecting the signal from the outside, couldn't get in, but by definition, it also keeps the signal on the inside in. You can define an area very well, and that's been used industrially right now. Some of the defense manufacturers don't like Wi-Fi because it's too insecure, but are actually looking at 5G because they can define an area within a building and then control it and then use it for all those different things we talked about earlier. So it's good. Jason, do you have a...
Yeah, just another question. So, you're talking about developing equipment, for the release 15, but then for release 16 and 17, is that going to require a different set of equipment? Do you have to then replace everything that you've put up for release 15? How much, what's sort of the economic life then for the equipment then for each release.
So if replacing could be, is it a complete hardware replacement? Is it a firmware update? Or is it just straight old software?
Well, I mean, the hope is that you don't have to do a hardware replacement. I mean, you just add features as you go. You don't have to drastically change, remove stuff and put stuff in. So as you go, further into releases, you're basically adding more features to the network. Just like LTE, like right now, you started, for example, with the release 8 or release 9 or whatever, and then you're adding features from different releases as you go, and then you can have like more software updates to your base stations. So, I mean, 5G is not only about the physical network, or it's a whole new thinking about the whole network to make it kind of more modular, more virtual, more prone to change as you go. So kind of make it more virtualized in terms of core and in terms of RAN, and making life easier in terms of just use general purpose hardware and add software updates to it.
Hopefully it's all software upgrades, right?
Yeah.
Don't touch anything. It's probably unlikely. I think actually it may not be radio issues. I think it's more likely to be antenna related as we get into those. And again, for the reasons we talked about earlier, not necessarily a release 16 or 17 issue, but related to other bands and things like this that have come in the meantime as well. So your one-touch strategy, for example, just go out, touch the antenna once and do all this, touch the tower once and do all this work. It looks like it's all related to 5G, but a lot of it's actually because you've been stacking up things waiting to do it once, right? So
yeah,
there's
one more thing I wanted to add on the millimeter wave advantages we didn't get to talk about, and you mentioned in your presentation this need for fiber. So one thing that this beamforming gives you, using of phased array and having all this bandwidth, is that you can sometimes get rid of needing fiber to every single small cell. And this is something that is called self-backhauling in the standards, and we call it integrated access and backhaul. This is something that AT&T is very interested in. Is basically you don't have to deploy fiber to every single tower. Towers can actually backhaul each other, and that you can use, on the same spectrum, just by, taking advantage of this beamforming, new beam steering capabilities of millimeter wave.
Question is how many is not all? Right?
I mean, yes, but
Yeah,
this is something
right.
that is possible, and it saves a lot of money. And
bless you.
yeah.
So you may not need fiber all the way through every grid in Austin.
Yes, and I mean, deploying fiber is expensive, and as you said, like you can't kind of, this is where the fiber is, this is where I need to put my small cell, right? So, so just having the ability to actually use, millimeter wave to actually do the backhauling from one small cell to the other actually saves a lot.
Right.
Sorry. I guess I need clarification on that. So you would need fiber to each cell, but not necessarily connect those two towers together?
So right now, you don't need fiber to every tower. So you can have the towers talk to each other through wireless, basically.
Oh. Okay.
It depends on
So it's like a multi-hop. So to get to the user, you actually go through 2-3 towers, for example.
When we talk about 5G and the release of 5G, we're talking about millimeter, and we're pushing it down to the different spectrums. What are the trade-offs of having 5G at the lower spectrum versus the higher spectrum? Is it just latency?
I mean, there's a lot of things. Higher spectrum. I mean, in millimeter wave, you get a lot more bandwidth. You get to have 20 gigabits per second peak data rate, hopefully. With lower frequencies, you get more coverage. You can, cover bigger areas. Depending on your application, you can use whatever spectrum you have available and kind of what you really need in this particular area for.
So your question, I think, is if I put in 5G at 600 or 700 megs, right, what will an end user see differently from LTE release 14 to release 15?
Oh, well, I mean, it's not, again, like, 5G is not only about the spectrum. It's actually, we are making changes now. Well, FDMA, we didn't make changes, but hopefully waveform beyond 52.6, maybe it's going to be different. But a lot of changes happened to the air interface. It's more flexible, more forward, compatible. You get different numerologies. You can go. The transmission time can be smaller, or you can use smaller kind of mini slots, which is like smaller opportunities to transmit rather than just confined to this particular frame structure that we used to in LTE. So a lot of possibilities are there to make things better. And this you will see from if you're using 600 megahertz or if you're using millimeter wave.
Right. So if you put it, the way I understand it is in LTE up to release 14, if you've got this much spectrum, then it's all LTE, and you're kind of confined to that in what you can do with it as an operator. Release 15, if I've got this much spectrum, I can say, well, this much is going to be LTE, and this bit I'm going to use for other things like IoT, and I can vary it. I can be more flexible with how I use that available spectrum. So therefore, I can do more things for the end user. The end user's connection necessarily may not change. You still have that Netflix, and you wouldn't notice a difference. But the operator's efficiency and flexibility and what they can do with it changes. And that comes, remember that slide I had about cost of operation, right? Flexibility comes from that. It's much more flexible, and that's what they gain for it.
And flexibility is important when you have applications like you want to watch your Netflix, but you also, I don't know, you have an urgent message to go through with ultra reliability or low latency. So you have the ability to actually package all of that in the same kind of transmission and send that, which is very important for all these applications. Because, I mean, 5G is no longer about just making your phone faster. It's more about enabling all these use cases that we're talking about. I mean,
a lot of the 5G stuff is not really related to the air. I mean, the millimeter wave stuff's interesting. Obviously, the air interface opens up opportunities. It's the architectural changes in the back end as well, like with low latency, edge compute, all the release 16, 17 stuff. It's fascinating. So, all right, we need to wrap up here. So, Prof. Heath, you're going first on this question, just to let you know. We'll work down. And you don't know it's coming because you haven't known any of these questions are coming. What keeps you awake at night? What is it that worries you the most that we as an industry are not addressing? And you've got a different timescale from these guys, I know. But what is it that worries you that could come back and go, darn it, I wish I'd done a PhD thesis on that in 2019. What is it you're concerned with? And obviously for you guys, what is it we're not addressing today that's going to come back and bite us in a few years' time? So there you go.
Well, that's a nice softball to end the panel. Thank you. I mean, I think, I don't sleep at night for personal reasons, but
I was gonna say that.
Industry can't solve that. I think the issue I have is I really have concerns about the way that the antennas are being used in 5G, the beam-based approach, and I just feel like it can be much more efficient. And they rushed to market and said, let's pick this, beamforming technology that was in principle invented, in the 60s, if not the 40s. So I think it could have been much better. And so I'm worried that a lot of these awesome applications are actually not going to work well because there's so much overhead associated with maintaining the link, and that isn't really been, I know I'm sure it's going to work, but I don't think that's necessarily been accounted for when selling the prospects of these rates, right? When you say 20 gigabits per second, that's neglecting all the overhead required to make sure the beams are aligned and pointed. So I think that's my main concern, and I think we've developed good solutions that could be used to address this, and I hope we have the chance, and that work doesn't get thrown by the wayside. And So that's my main concern.
Okay, good.
Just to kind of dovetail on that. So one thing that PHAZR is actually doing that is a differentiator in the industry is whether everyone in the audience knows or not, there's kind of been this technology push forward for beamforming called hybrid pre-coding. Essentially, you're taking old analog beamforming, you're combining it with what we actually did, I don't know, 10 years ago with digital beamforming, and Robert had a lot of work on making sure that the training of those beamforming systems is very, very efficient. And but our perspective is that actually you can do fully digital beamforming. The reason that we went to this hybrid pre-coding is because we thought the complexity would be too high for digital, too much cost. But actually, as things have scaled, we don't actually feel that's the case. And so taking advantage fully of digital beamforming, it's possible to do that in the standard. So the standard doesn't necessarily prevent that. Right. Maybe you want a little bit more efficient signaling protocols than what's there, but that's debatable. But I do think that you will see that more and more going forward. More people taking advantage of fully digital beamforming. To address Ian's question.
So you should be able to sleep at night. There you go.
Excellent.
I don't know if you trust me enough, but anyway. So to address Ian's question, the thing that bothers me the most, or not bothers me the most, that I have the most uncertainty about is, we have a lot of promises about how 5G is going to go. We talked to a lot of operators about how they want to deploy, but how hard is it really going to be for them to deploy the millimeter wave technology at scale? We want this to be a successful technology. We want it to be scaled out in a very high dimension. But how hard is it going to be? The deployment architecture is completely different, right? I mean, we saw with small cells how difficult it is to get these base stations in really small locations everywhere. You have all of these logistical issues associated with that. And then there's also a lot of people concerned about safety with millimeter wave, whether it's rational or not. It's out there. It's in the news. People are concerned. They don't want this in their neighborhood. They feel like there might be health effects. There was somebody was telling me that they had like a base station that was not even turned on near their office that they had been trialing with 5G, and they had turned it off after the trial was over. But people in the office were still complaining that the 5G base station was giving them headaches. So I mean, there's this paranoia associated with 5G, and I fear that something like that will impede the technology from being successful quick enough. So that's one of the things that concerns me.
Good. You had the first word, now you get the last.
Yeah, I guess my comment will be more on the industry itself, like at least from a general comment on the standardization process. We see from, we get to talk to all vendors, all operators all around the world, and it's what I want to see is more technology being pushed in the standard and more kind of new stuff coming and solving all the issues that we're talking about, and at a faster pace than what is right now, because what is happening right now is things are being slowed down a lot by IPR war and a lot of politics between companies, and maybe in an ideal world where actually technology is being put forth to help solve all our connectivity problems without dealing with everything else would be nice.
Okay, great. Thanks. Thank you. Thanks, panel.
Thank you, guys.
Thank you.